Good morning, and welcome to the Quantum Technology Training for Policymakers. Today, we are going to talk about a particular investment from the European Commission, which is going through the CHIPS Act for technology. And we have a lot of speakers today, so we are waiting for an exciting session ahead, and we will straight away come to the talks. I would like to thank QCATS, the Coordination and Support Actions of the Quantum Flagship, that is organizing this training, and the National Institute, Italian National Institute of Optics, for helping to prepare this training. So straight away, as we have a lot of speakers and interesting content, I would like to invite our first speaker, Andreas Tortschanoff, to come on stage and share his. And Andreas will present us the trapped ions platform for the pilot line for quantum technologies.
Okay, thanks.
Yes. Thank you very much for being with us today. And Andreas is the principal scientist at the Silicon Austrian Lab. Please welcome, and we are looking forward to your talk.
Thanks for the introduction, and thanks a lot for giving me the opportunity to present our ambition to set up a European advanced manufacturing pilot line for ion traps within the CHIPS Act framework. Also, be aware now we are jumping directly in medias res in presenting the ion traps rather than the introduction of CHIPS Act. I hope that Kristiaan will join later and also introduce about the general framework. Besides the strong competition on quantum technology for the ion traps and for many of the chip scale quantum technologies, we have the challenges of high inconsistent quality and large fragmentation of technology landscape for the ion trap chips, where different technologies are still used, and definitely no PDKs or standardized interfaces are yet available, or standardized validation even to compare different approaches. And also quite specific to ion traps is really the need for, in order to scale up, to provide ion trap chips with scalability, really advanced functionalities have to be included into the trap chips, in particular integration, getting the photonics and electronic parts from the lab really into the chip. And the challenge in this context is also the long iteration cycles for advancing the technology due to the complexity of the fabrication and the complexity also for the testing characterization. And that's the framework where Champion wants to play a strong role. The consortium, we could group 21 partners from 6 countries. We're quite proud that all ion trap companies basically took part in our proposal, all eligible ones. We were supported for 27 letters of interest from different companies and groups, which really shows the interest. As Kristiaan will also outline later, we expect in the first phase a 3-year project starting. We aim at starting next February. We expect funding up to 50 million euros, and that's funded by EU and member states co-funding, and should be the first phase of a long-term strategic action plan. The objectives we defined in Champion are really the setting up of an accessible to all European stakeholders, accessible and sustainable high-quality pilot line. Also to foster, include and foster ion trap chip innovation in the field, of course, ensure the European supply chain development, provide quantum PDKs for scalable and efficient production, work also on industrialization and strategic roadmaps in the field of ion traps, also defining the key performance indicators for ion trap technologies within the project, trying to reach them, and also the roadmap and the visions ahead. Let me give me a little intro to what we plan, to the plans. The Champion goal is the accessible, high-quality pilot line, which will be centered around central services we want to provide, including standardized ion traps and the PDKs to fabricate with high reliability and quality ion traps. We will include three technologies. We also, of course, will foresee customized traps to provide traps going beyond the PDKs and more advanced features, and also will provide the access to the capabilities and to the individual processes and the capabilities of the partners. The access, and within the project we defined more than 10 use cases at the moment in having playing role in all of the quantum technology pillars, not only computing but also metrology, sensing and communication. We will cover with our use case partners. Access to the pilot and services is planned through a single entry point, where we really hope that it becomes like a central hub for any Antwerp requests in the EU, and which will be also linked to the design platform to provide access via the design platform on European level, and also strongly linked to the competence centers in order for outreach activities, for trainings, and this kind of stuff. And also, of course, linked strongly in the EU ecosystem to activities going on within the other quantum pilot lines, which will be presented just after one, I would expect, which will also start next year. Also to already running activities like quantum flagship projects, also the experimental pilot lines, Q-pilot, Q-test, where some of our partners are involved, where we expect strong or want to foster strong synergies. And of course, active role and coordination, also with standardization bodies and different quantum activities and concepts. Yeah. I didn't forget something, but let me highlight again the like champion value chain, or the consortium, which makes this project possible, and which enables us to really go in the value chain for quantum chips, including design, fabrication, also testing, packaging, and validation, in order really to provide customers with tested working quantum chips to really reduce the entrance barrier into the field and really enable progress. And as I said already, the internal use cases which we receive the chips, and with the use cases defined to validate the usefulness and the real world, basically, application and potential of the chip. As I said, the line is coordinated by Silicon Austria Labs, this pilot line with main foundry partners at SAL in Finland, which is also great to have a strong, really foundry partner inside the consortium on a very playing a strong role, and really providing a good vision for industrialization of successful results. Strongly supported by additional fabrication facilities with expertise in ion trap and special processes. And as I said, 21 partners to really enable the whole value chain. And with that, I'm basically finished. Thank you for your attention, and looking forward for questions at the end, if I remember right.
Thank you very much, Andreas, for a very focused presentation about the ion trapped pilot line. And I would like to invite straight away to the stage Nicole Fabbri, who will present us today the pilot line based on diamonds. Nicole, please welcome to the stage, and let me ask you to share your slides. Nicole is the senior researcher at the National Institute of Optics, CNR-INO, and also in the European Laboratory for Nonlinear Spectroscopy, LENS, in Italy.
Thank you, Oxana. Thank you for the invitation, for, let's say, the opportunity to talk about the direct project for diamond for industry-ready quantum technologies that I coordinate. let me just start introducing a little bit what are the peculiarities of diamond quantum technology that differentiate this kind of technology from others. I would start. A first factor is that Europe is currently in a unique position of leading the diamond technology and research and innovation, with pioneering research that has been performed here in Europe. Currently, startups focus on the development of diamond quantum devices are flourishing across Europe. Big companies are investing on this kind of technology, and at the same time, there are really big investments all around the world, in Australia, UK, Japan, and the USA, of course. The second factor is that diamond technology span, let's say, all the three quantum technology areas of sensing, computing, and communication, with multiple use cases in all these three areas, and many applications, I would say, of national strategic importance, for example, in defense and security. Remarkably, diamond sensors offer great advantage across microsensing and macrosensing, with use case in navigation, radio frequency receivers, magnetography, and so on. With let's say, they can be deployed throughout defense, automotive, medical operations, and so on. They are, let's say, there are architectures, proposed architecture for room temperature and cryogenic quantum computing, based on diamond, with a clear path towards mobile computing in vehicle and satellites, and additionally, diamond quantum repeaters and interfaces may be key enabling technology for quantum networking and the quantum internet. So diamond quantum technology are in a little bit unique situation of addressing application in all these areas. And this opens a really large market opportunity that is low risk because it is really diversified. The approach we pursue is translating the diamond quantum technology innovation and lab scale production from the current situation of expensive, non-standard, low volume components into really robust and scalable production of diamond quantum chips. So the trajectory is focused on converging a set of devices with components that are associated to different functionalities, depending on different use cases. So the concept is here on the right, with a vertical architecture where we have several layers, high purity diamond chip with integrated color centers inside, optical and photonics layers, magnetic components, and chip scale integrated electronics. So this is meant to be a modular architecture that provides all the key elements that are necessary for quantum devices that can be adapted to different applications for different use cases. So to pursue this goal, of course, the current challenges regard overcoming the current fragmentation of the supply chain, while expertise already exist and are strong across all the value chain. They are often fragmented across countries and institutions, so we have to consolidate the resources. Also, the current production is small scale and has to be, let's say, scale up, requiring advanced tools, of course, miniaturization and integration of the component and devices, another challenge, as well as the standardization of processes and overcoming the current variability of properties and device performances, and also the access to advanced manufacturing tools. So, and last but not least, the bridge from academic research to industrial requirements that are not always aligned, and they need to be, this link has to be strengthened. So the quantum diamond chip pilot line aims at consolidating the value chain from the diamond quantum material to the integrated device, achieving a higher TRL MRL level, integrating the testing and experimental facilities in the pilot line, providing a seamless, let's say, production and testing service, strengthen the collaboration and innovation within the Europe diamond quantum ecosystem, and create a sustainable and open access framework to support accelerated development and market introduction of the next generation devices, up to, let's say, transitioning this pilot scale production into diamond-based devices that are really industrial ready in terms of maturity, in terms of scalability, to meet the needs of quantum industry over the next decade. To reaching this goal, we have assembled a consortium of 32 partners spread out 14 countries, and including SMEs and big industries, so that all the diamond quantum technology value chain is covered, and we connect with the existing piloting infrastructure and initiative in Europe, remarkably with the previous project of Q-Pilot and Q-Test that already include pre-commercial small-scale production and testing capabilities for diamond raw material and diamond-based devices. And here we want, of course, to mature these manufacturing processes and increase the size, the production volume, and the process standardization. So to reach the ambition of DART, this requires to develop optimized and upscale diamond technologies at the level of material, components, and the integrated quantum chip device. So each level builds on the previous one, ensuring a systematic and modular approach towards the development of quantum devices. At the material level, we aim at developing tools and processing for producing high-quality diamond material, including diamond substrate growth, color center generation. And at the module level, we will introduce device-specific designs, simulation, process models, and the fabrication of the modules, covering the optics, the DC and AC magnetics, the integrated electronics. The device, importantly, will focus on combining the individual modules through wafer and die level integration and system level integration. This will be complemented by testing and validation framework that will allow to, let's say, will ensure the functionality, the reliability, and maturity. Up to the realization of demonstrators for specific use cases. To support such developments, we will establish a distributed network of pilot facilities across Europe that will include RTOs, university, and industries, SMEs and big companies, that will focus on the development of all the aspects that I described, integrating the competencies, and this will ensure, let's say, the federation of these partners into a unique pilot line will ensure developing parallel different manufacturing tools and approaches, defining quantum PDKs that will satisfy the requirement set by use cases. We will foresee both internal use cases, development by the partner of the consortium, and external use cases on commercial basis across the all quantum technology areas that of computing, sensing, computing, and communication. This is, let's say, an overview of our direct pilot line project. So I thank you for your attention. I'm eager to answer questions during the questions and answer session. Thank you.
Thank you very much, Nicole, for the very focused presentation of the direct project, the ambitious plans, and the huge consortium. And I would like to welcome now to the stage, to open the camera and share the slides, our next speaker, Pepijn Pinkse, who is the professor at the University of Twente in the Netherlands. And Pepijn will present us today the pilot line of photonics for the quantum technology.
Yes, thank you very much for the introduction. I hope you can see my slide.
Yes, it's all fine.
Perfect. Good. So indeed, my name is Pepijn Pinkse. I'm the coordinator of photonics for quantum, P4Q abbreviated, and I'm from the University of Twente in the Netherlands. Let me reduce this view. Yes, the photonics for quantum pilot line is based on the notion that photonics is the key technology for most quantum technologies. So if you look at this overview here, you see that there are at least 3 different quantum computing platforms that require photonics. First of all, there's let's start on the upper right corner. Let me see if I can get a mouse laser pointer. Yes, trapped ions, as already introduced. Ions are typically trapped by radiomagnetic radio frequency fields, but they are addressed by optical fields. And at the moment, lots of these the beam shaping and beam formation is done with free space optics, and it doesn't scale. And I think there's consensus in the field that we will have to work towards miniaturizing and introducing integrated photonics in trapped ion quantum computing systems. Same holds for neutral atom quantum computing. There are typically whole gratings defined by optical fields where atoms are produced or sent into readback states, and they also need to be addressed by light fields, and there are many of them, and therefore integration is also there. Integration of integrated photonics in the neutral atom quantum computing environment is paramount for further scaling of those platforms. You can also build universal quantum computers completely based on photonics, and obviously there photonics is the key technology for realizing that. There are several big players there. I think most known worldwide is PsiQuantum, but we have European partners as well, Candela, Quix Quantum, and they rely very heavily on the further development of integrated photonics to have the technology available that they need to build these quantum computers. There's also quantum communication requiring photonics. Obviously, in quantum communication, once you start communicating at large distance, then you need light. So handling light in all its aspects is important. If you do quantum communication, you want to manipulate light on the quantum level, single photons, squeezed light. You work with single emitters like the color centers, diamond color centers we'll also discuss today, or pure photons in terms if you work with quantum key distribution systems, for instance, that are based on send and measure, prepare and send systems. Also there, integrated photonics is important for scaling up these things. For instance, into satellites, you want to make the system as light as possible. So again, you need integrated photonic chips with low loss, high complexity, and very high level of maturity. And also for quantum sensing, quantum sensors can be based on cold atoms, also other techniques. And again, these atoms need to be addressed by photonics, and you need many of them. And to make this scalable and cheaper, you need integrated photonics. So in a nutshell, we need highly specific photonic integrated circuits for these 4 qubit carrier types: single or entangled photons, neutral atoms in Rydberg states, trapped ions, and for color centers. And therefore, the goal of this pilot line is to design and stabilize production processes of various building blocks for all of these different computing, communication, and sensing platforms using highly specific photonic integrated circuits. Now, integrated photonic circuits are already designed for and developed for many other applications. Think of classical computing, or also classical telecommunication industry. So there is already an industry there developing these things, but on top of that, we need additional functionality, even lower losses. I mean, there's hardly an application that is so demanding on the losses of your integrated photonic system as quantum photonics. And therefore, developing these low loss, non-standard wavelengths, telecom is typical for most applications, but if you want to communicate with interface with trapped ions, color centers, and neutral atoms, you need to address those particles in their resonant states. So you need often colors in the visible or even in the near ultraviolet or blue region of the. And these are very special wavelengths for integrated photonics, and therefore also developing those wavelengths is a part of this pilot line. So the overall structure of the pilot line is the following. We will use the input of the users inside the consortium, but also of other pilot lines like the trapped ions pilot line, the color centers pilot line, the diamond pilot line, and the neutral atom pilot line for as input for specifying the user requirements for these integrated photonic circuits, so that we can develop new photon sources like quantum dots or nonlinear optics, new nonlinear optical quantum light sources, color centers connected to integrated photonics. We integrate them on chip level with the standard photonic integrated circuit platforms, but developed specifically towards our targets. So the standard platforms are silicon nitride, which is a very transparent platform for integrated photonics. There's thin film lithium niobate, which is a platform that allows to modulate your light very fast. And the new platforms coming up like aluminum oxide, which allows you to go further down into the blue or even the UV parts of the spectrum, which is necessary for some of the ion and neutral atom systems. And we will integrate this on chip with modulators and detectors, even superconducting detectors to detecting of photons. And this all needs to be integrated, and there's still a huge effort to improve these integration techniques and also make them more scalable and more mature, so that the throughput and the yield is higher. Of course, you also need packaging. A chip, naked chip is not enough. You need to package it in a way that is compatible with the requirements for photonic quantum computing, communication, and sensing. That is often low loss, compactness, temperature stability, etc., etc. And at the end, of course, chips based or produced in this pilot line should be tested by the users. So we've set up a consortium with 29 partners at the moment in 12 member states. All the logos are all listed here. It will be coordinated from University of Twente. What is, I think, special in this pilot line consortium is that we have a lot of companies involved. There's only a few academic institutions. Well, for instance, in the Netherlands, we have University of Twente, who actually owns the clean room that is used as a as a production facility for companies like Lyonics. That's why there are a few universities there. But as you see, there are many quantum startups, but also there's Thales and Leonardo as big companies, and many other specialized spin-offs and scale-ups that work on specific integrated photonic platforms for quantum technologies. We have organized the pilot line into 5 to 6 use cases. Listing them from near infrared to UV. We have quantum computing using photons, quantum communication using 3.5 sources. These are gallium arsenide sources producing telecom wavelength entangled photons. Quantum communication using color centers, diamonds. Quantum sensing using atoms, and there is the neutral atom and ion trap computing efforts with their specific wishes for photonic integrated circuits. So the expected outcome of the pilot line is that we will, after the pilot line has been set up and developed, we have a distributed physical pilot line, a physical infrastructure in Europe that comprises the manufacturing sites at different parts in Europe, where the production facilities are so further developed that we have come out of the situation that we are now, that most of the production of these specialized chips is very academic, low volume, low yield, to a situation where we go to from several to many to a lot and a whole lot, so that in the end you have PDKs and ADKs developed, so that people also from outside the pilot line can order parts that they require for the quantum technologies, for all of these with all of the techniques developed in this pilot line, and that the processes are in place, that we have industrial manufacturing. Maybe not the volumes that are known, for instance, from the telecommunication industry, but at least the yield and the professional way of production should be there after this pilot line has been successfully implemented. Maybe a last comment about another already granted and running pilot line, that's Pix Europe. That is a pilot line not for quantum, but for developing integrated photonic systems by itself, but focusing on other mass markets like communication and automotive, health, security, etc. Obviously, there are connections, but for almost all of these classical applications, the requirements for losses are not so stringent as for quantum. So we think we can piggyback on some of the development of foundries, for instance, and add the low loss capacity on that. This very specific wavelength colors, the specific integration strategies that you need to interface with all the things that you need in all these quantum computing, sensing, and communication systems. Okay, and I guess this is all the same for you. We have for the first SGA a total budget of 50 million euro that needs to be co-funded, half of that from the member states. Actually, we're in the process of negotiating that with the parties out, and also getting the co-funding from the states. Good, that's what I want to share. Thank you for listening.
Thank you very much, Pepijn, for the presentation of the Photonics Consortium, which I imagine will be interacting a lot with other pilot lines,
yes,
as this is a fundamental component. And I would like to then go to the next speaker that we have in the program, and it will be Kristiaan de Greve. And I welcome Kristiaan to come on stage, open his camera and share his slides. Kristiaan de Greve is the program director for quantum computing at Imec, and he is also a professor of electronical engineering and Proximus chair in quantum science and technology at the University of Leuven in Belgium.
Thank you very much. Can you see my slides?
Yes, but
Okay,
they are in the mode for presenter.
That is what I'm trying to do. So let's see here.
You're sharing the view that's supposed to be your view.
Exactly.
That's the problem.
I think you can go to display settings on the upper bar
Yeah.
and possibly switch the screen.
Where is the display
There's,
setting?
I see on your screen a display settings.
Yeah. Okay. Swap presenter and slide view. Here. This way? This works or not?
Not yet.
Still not or yes?
Still not?
No, still not.
Because and I'll stop share and try again. Because unless this gets solved. Otherwise, I'm just going to do it straight from the presentation. And then we will not be in presenter. Does this work?
Yes.
Okay, thanks. Thank you very much. Apologies for the hiccup. It's my pleasure to present SPINS, which is the semiconductor quantum pilot line. You'll see some similarities between the previous presentations and ours, in a sense that, okay, is this, start my video, is this thing, no, yeah. In a sense that SPINS is also trying to focus on an aspect of quantum technology that Europe has been pioneering and leading in, and it's particularly the semiconducting quantum technology for computing purposes, particularly based on quantum belts. It's one of the first platforms in Europe which has actually begun going into an industrialization mode already about 10 years ago, and we were leading in that in the world. We made the first industrial CMOS devices in Grenoble. It's also a field in which, for instance, the Delft group has been really pushing the limits worldwide in terms of fidelities, in terms of sizes of compute systems, with like a lot of innovation as well as startups in this space. This is also a field, and this is similar to what Pepijn was saying, where you can piggyback to some extent on the semiconductor industry, but of course with much, much, much tighter specs. So in Europe, we have this strength of a strong RTO ecosystem. And in fact, the previous CHIPS Acts heavily invested in those, in VTT, in Leti, in Imec, in Fraunhofer. So the idea behind SPINS as the semiconductor quantum pilot line is to make active choices, not to focus on everything, active choices and leverage the infrastructure as much as possible and focus on what is needed to take this to really high quality quantum chips. So SPINS, and just like everybody here, we've been fun and creative with acronyms. For us, SPINS stands for Semiconductor Pilot Line for Industrial Quantum Nanosystems. It made it over SPQR, which would have been the Semiconductor Pilot Line for Quantum Resilience in our internal vote. SPINS actively makes a choice. SPINS is not focusing on all sorts of semiconductor quantum technology. It's particularly focusing on quantum dot qubits for quantum computing. And it focuses on broadening the user base by virtue of actually providing high TRL chips via multi-project wafer process to the community. So our focus is really to build stable PDKs and execute multi-project wafers. Of course, we're just like the photonics presentation of my predecessor saying, we are building on the foundation of the semiconductor industry, we're building on the foundation of the RTOs, and we're focusing on what actually is needed to make the delta to the specifications, the tight specifications of quantum. So we're at a strategic level trying to make sure that the user base can be broadened by making sure that there's stable MPWs that both startups and also academic groups can work on. So the focus of the project is quantum yield and production. It's not a CapEx heavy consortium, it's an OpEx focused consortium. We are leveraging infrastructure to the maximum extent. That allows us to have higher ambition. So why are we doing this? By focusing on silicon and germanium quantum chips, and on the core of it, we can strengthen Europe's leading position. We can be ambitious. We can go to full PDK development via multi-project wafers. We can create multi-access, widely accessible technology in a somewhat affordable way by reusing infrastructure and investment in processes, maturity, and PDKs. What we don't know is what 10 years from now will be the dominant platform in this entire semiconductor community. So we are mutually de-risking several platforms between germanium, silicon, silicon germanium, and silicon MOS. Platforms which are close enough to each other that we can develop them jointly. We can do a combination of mutual de-risking and have mutual learnings between them and make sure that there is overlap between everything we do. So these are not independent developments. These are mutually de-risking developments with as much overlap as possible, joint work packages. So we have commonalities which we reuse, we have learnings which we reuse, we have a testing strategy which covers all of them together. So we develop a common approach in Europe. We are standardizing all of this technology, which is a risk mitigation strategy from a strategic perspective. And similar to what several predecessors have been saying, we will also have two phases. We have in the first phase, which will be the focus of the SGA that is currently in preparation, have a preparation trial MPW, which will have a combination of lead users and test users. And then afterwards, we will have an execution MPW, which is open to the entire community. We combine both RTOs, industry, and startups. That is the core of this proposal. So this is not a university-heavy proposal. This is a RTO startup interplay, startups providing the specifications, RTO and industry executing, with a goal of bringing this to a real market. So it's a project which over these three platforms creates a cross-platform approach. So we are standardizing our characterization and metrology approaches, all to make sure that the PDKs we develop are actually relevant. We are standardizing our process development as much as possible. Now we are leveraging the infrastructure in which Europe has invested so much. So similarly to several other consortia, this is also a pan-European collaboration. On the SOI Silicon MOS side, it's the main players are in France and Finland, so VTT and Leti in combination with Semicon and Quobly. So the interplay between RTOs, industry, and startups is heavy there. On the germanium silicon side, it's Imec TNO together with Greve and TU Delft, which are the main players. And on the silicon germanium side, it's Infineon with Fraunhofer and startups in Germany, which are forming the interplay between production and specifications. With an across the board contributions from Czechia, Spain, Portugal, and Italy to ensure that wide use of these chips is possible. So what's the rationale between those chips? The rationale is that at a strategic level, multi-project wafer, so easy, low threshold access to high-level technology is important, which will allow expanding and enabling the broad user base. Because let's face it, we still need the ideas in quantum. We're not there yet from a compute perspective. So we want to make sure that the people who have those ideas have access to the high-level, high TRL technology such that they can develop those ideas much, much faster. So we have the sophisticated lead users to help steer the PDK development to make sure that what we make is relevant. We're providing a technological backbone, and we're lowering the barrier to entry to ensure a form of fabless operation, with the key players of Fab 1, of the phase 1, being some of the main European startups in this space. And then in this phase 2, we want to broaden this user base by having stable processes, include academic users, which are the future startups, the future idea generators. And in that sense, we're going to be making sure that we're more ambitious than, for instance, is happening in competing geopolitical entities, like, for instance, the LPS Qubit Collaboratory in the US. So thank you very much.
Thank you very much, Kristiaan, for the very focused presentation of the semiconductor pilot line. And I would like to go straight to the next presentation, which will be done by Alexandra Paul, and she will be presenting the neutral atom pilot lines Q-Planet in this presentation. Alexandra, thank you for coming on stage. I will now.
Thank you, Oxana, for that. Good morning to all. So I will be discussing with you indeed the Q-Planet quantum pilot line. That is the quantum pilot line for production of advanced chips for neutral atom European technologies. That's what Q-Planet stands for, and is based, so indeed, on the neutral atom platform for this pilot line across Europe. Next slide, please. So perhaps to give you a bit of context for this presentation, And for this pilot line, why did we decide to present this pilot line at European level? Is because we have seen recently, if I can say so, the neutral atom platform that some might have considered as a late boomer in the field, as really having drastic advancement and progress across the 2-3 last years. And this has been true, as you know, for quantum computing, for instance, where industrialization has already started across Europe and the world, with already some quantum processing units already industrialized and on-site in different countries, such as France or Germany nowadays, but also globally, for instance, also in Canada. But also because we have seen that also for quantum sensors, the neutral atom can also be very key. Notably when we look at different type of application for instance, for accurate atomic clocks or magnetic field sensor and gravimeters, where here we have seen a lot of progress in the last, of course, 20 years, but where there is still a challenge based on the use of neutral atom to notably decrease, for example, the size and the mass production of the different devices. And this is also a challenge that is still today in place that needs to be solved at industrial level. And of course, neutral atom can also be a key technology as well for quantum network today, and especially having a major role for the development of quantum repeaters and quantum memories. So really, the QPlanet pilot line has this ambition to be across the 3 pillars as such, from the quantum value chain, so really quantum computing, sensing, and also communication on network, because we see that is the platform that can nowadays really evolve, has been evolving, has still some challenges, but is at the maturity level to really go to industrialization at scale if we manage to solve some of these challenges, and notably based on different type of chips that can be produced in this quantum pilot line that I will come back in a moment. So here what we see in that context, as I was saying, yes, thank you. But so the slide before was really on the context and saying that we have these 3 major challenges to address based on neutral atom technologies for the quantum pilot line, and that chips can support that are really the capacity of the technology we use, the reliability and the scalability of that. And this is where chips can support the development of neutral atom platform from computing to sensing via communication networks as well. So in the QPlanet, that's why the main objective is to go through the 3 pillars and to work on the 3 pillars. This, I think, it has been clear now from the introduction, and really focus on 3 main aspects for the production at scale, at industrial scale. So one of them is really trying to have the development of what we call these atomic chips, that this will actually, for instance, help us in particular to develop and integrate key components for better manipulating atoms ensembles that can be for atomic cloud generations, that can be also for atom trapping, that is going to be easier to be done based on chips, for instance, instead of, for example, taking some beamers today to try to manipulate the atom and then using the technology for the trapping, for instance. So this is going to be something that is important, and that we will come back in a second in the next slide, where there we would like to go mainly to develop some physical packages, notably for atom chips, such as also vacuum cells component, and we'll come back to that on the technology that we have decided to use, and where we really see an opportunity based on this atomic chip to really miniaturize and integrate the physical packages for a range of quantum devices such as atomic clock, magnetometers, and inertial sensor, for instance. And this is going to be what this use of chip is going to be a very insightful to go to industrial production. The second part is really to look at what we call more this on-chip laser system. So based on this neutral atom platform, as you know, we use a lot some lasers for doing the calculation for quantum. And here what we see is that on one side, we have a challenge of size. Lasers are massive, for instance. So some of the functionality of this system could be actually made on chip. So it will help us to support what I was saying before, this miniaturization of the technology much more, for instance. But it's going also to be something very useful for improving the performance of the different system. Given when you have many different lasers, you need also to do many different alignments between the lasers, and sometimes you can lose in terms of reliability as well. So you have some challenge there. When you do that on a chip-based component, is going to be much easier actually to align. The system is going to be also more compact, and you are going to also win in terms of reliability of your system. So that's something that we see is going to be also improving the performance of the neutral atom platform as such. And also, you will also be able on chip to be able to support the multiplication of different lasers output. So it's going to be much easier to target much larger amount of qubits on chip than what can be done today with bulk of massive lasers. So that's why we see the two as complementary. Sorry, just a second on the other slide. As on one side having really this way of better actually manipulating, trapping the atoms with the atomic chip, and on the second part having functionalities that we have for the use of the lasers to be on chip to improve as well the reliability and improving also the performance of the qubit that we can get. And most importantly is that if we don't, in addition to that, also be able to actually produce and assemble the different electronic controls that serves actually to activate the different active component that I was mentioning for on-chip lasers systems, like the amplifier, the modulators, then we would not be able to use at full scale this technology that will be produced, notably to develop different use cases in different domains that can go from drug discovery to for instance, weather forecast as well, that we would like also to be able to deploy within this pilot line as well. So the three components are very important to really make sure that the neutral atom platform go to quantum industrialization and production or across the value chain, the three pillars, but also that it can already start to be adopted, of course, by different end users via the different applications that will also be part of the pilot line, via notably the importance of the electronic controls that will also enable to activate again the on-chip laser system to then enable the different use case. So I think it's also clear then why we go in the production cycle from the design until the end user here. So next slide, please. The next slide also summarizes what I was trying to explain to you, that it's really important to understand QPlanet as an holistic project, in the sense that it covered the three main pillars of the value chain for quantum based on this platform, as I was explaining at the beginning, trying to basically overcome some of the main challenges that can be a bit different from quantum computing or quantum communication or sensors, but that overall will serve the three of them. Let it be for the reliability that needs to be improved, the scalability, that also need to be improved. For instance, for some of the neutral atom platform used over these 3 segments, or even what I was saying, the miniaturization and integration of the technology. Next slide, please. So now to give you a bit more of detail on these 3 different production, if I can say, main pillar that we have in cuPlanet, as I was saying. So the first one is really to advance on the development and the production of atom chips, as I was saying, that is different from what we see notably today in the state of the art and what exists at the moment. Here, as I was saying to you, we have some needs to really improve the manipulation of the atomic ensembles, and that's why, as you see here, we will be working on developing, this atomic chip that will enable to actually have this functionality of atom trapping and transport that will be on chip. That's not the case today with our partner from STIRT, for example. I'll give you some example, but also to really improve what we call the atomic cloud generation in vapor cells as well, for developing, for instance, more compact clocks. That is in another aspect, but also to be able to improve the manipulation of atom in cold vapor glass cells, for instance, that we need to do that as well for different type of application in the pilot line. So this is the type of the 3 key family of technology component that we have been selecting for this pilot line on the development of for the production of this atomic chip. And that is going to be important. Today we see that there is some type of maturity level already at TRL 4, but here the objective is really to go to industrial transfers and go much higher in terms of TRL. Next slide, please. The second part, as I was saying, is really on the production of what we call this cheap laser system, where we will have the possibility again, as I was explaining before, to have some of the functionalities that we use with bulk of laser today available on chip. That will enable us notably to improve not only the performance of the system, but also the possibility to have more reliability into the system and also of the integration. And that's why there we will also focus actually on developing low noise laser sources, the amplifiers, the different type of frequency modulators that could all be integrated, as you see, on a single chip as well. So the combination of the 2 are quite very important. Then can we, go to the last slide? So as I was saying, and then the electronic control is much important as well here, because without activating this electronic control, you cannot actually activate, some of the component, as I was saying to you, some of the active component when we look at the specific optical component that we want to develop on chip for system lasers. And this is really important to make it in place, as you see it. Otherwise, then we can't activate the system. We can't be then able to basically use at full capacity the neutral atom technology based on the chip, and we cannot then enable some use case development that will also be part of the pilot line. And as you see, the electronic control is underneath to both. So as I was saying, the active component from the different specific optical component that we will have, but also for the part on the atomic control chip. To control this is very important to also develop this electronic control here. Next slide, please. For the sake of conciseness for this presentation, so these are the 3 pillars again that we will be developing from the atomic chip, from the on-chip laser system, and the electronic control that is going to activate both chips to use better neutral atom technology for the 3 key pillars, so from sensor, communication, and computing. and then enable some of the use cases for end user within the pilot line. And this, we are going to be doing it with 37 partners across 12 countries that you see here, the different countries that will be involved. What is very important here to also underline is indeed this is going to be led by Pasqual, that is, as you know, a quantum provider for based on neutral atom technology across the globe today. So from an industrial player that is also a startup, but this will also include, of course, an important part of other industrial actors that will be part of this pilot line as well, and also a strong RTO basis. So the importance to have still both, but having this mindset to really go to industrialization the quickest as possible, be useful for the end users with a strong also leadership base led by a company in the field already operating today into delivering some of this quantum technology in the market. So that was very important for us. And a point that I didn't mention much, but that is also critical, that will be indeed notably developed by our Portuguese colleague in the consortia, will be as well the importance to monitor the energy performance actually over the whole cycle of the Q-planet, of the different activities, the energy performance of the work and the activities and the production that is going to be done. And this is absolutely important because the neutral atom platform can present some advantage also in terms of energy efficiency. And we would like to make sure that this is monitored during the whole project to ensure as well that the technology is used while preserving the planet as well. So I stop here and I thank you for your attention and happy to take any questions.
Thank you very much, Alexandra, for the presentation. Alexandra was representing the Pasqual company, and she's the global lead, public policy lead at Pasqual. The next speaker that we have on the agenda today is Pekka Pursula, and I welcome Pekka to go on stage. And Pekka will present us the superconducting pilot line project that is called Supreme. And I would like to remind you that you could put your question in the question and answer tool, and apologize in advance that we are going over time today, but we have a lot of interesting insights and we hope you will stay with us. And we count on closing the session at 12:30 today. Pekka, you're very welcome to present. Your video is missing.
Okay, thank you very much, Oxana. So my name is Pekka Pursula. I'm a research director at VTT on Quantum Technologies, and I will be presenting the Supreme superconducting European quantum pilot line today. So let me check now. And yes, now I can change slides. Good. Okay, so superconducting quantum technology is one of the most mature quantum platforms as of today. So its fabrication is based on well-known semiconducting fabrication methods and techniques and equipment. And then if we look at the quantum, let's say, application side, we have already today quantum processing units or QPUs with several hundred qubits and available and in use, and especially it's important that also the quality of the processors is good, so that Q-gate fidelities are in the range of 99.9%. So they are a platform, I would say, that in quantum computing it's the most mature and available platform for the end users currently. But what is superconducting quantum technology then? And what is Supreme focusing on? So we are focusing on the chip technologies, how to build superconducting quantum chips, and they look like this. So a 3D integrated quantum processing unit in a quantum computer. It's a silicon chip or a stack of silicon chips. Here we see an 3D integrated quantum processing unit which has several chips bonded together. And if we then open this box, we see that one of these chips contains the qubits. And the qubits are structures in the order of 100 micron size, and actually the quantum component in each of these qubits is a Josephson junction, which is a tunnel junction between two superconducting metals. And this is the basic building block of superconducting quantum devices. So in Supreme, we are looking into different superconducting quantum technologies. Actually, we have 4 different categories. So we're looking into the best possible processes for qubit fabrication, which is so-called angle evaporated junction process, which provides the highest quality as of today. We are then looking for more scalable options, which enable us to go from hundreds to tens of thousands of junctions and qubits in a chip, which is called the edge junction processes. And this is an approach which is also de-risking, as previous speakers have said, that quantum technology being in its early development phase, it is not yet clear which technology will be the one that then will be used in the applications in the long term and in the phase where we are talking about tens of thousands of junctions and qubits in a single chip. So we have kind of 2 flavors of junction processes. And then we have a very important part, this 3D integration process, so that we can build more complex systems using the superconducting junction and other technologies to build this kind of a 3D integrated chip stacks that I just showed. And then a fourth process is what we call the hybrid superconducting processes, and this supports especially detectors and sensors and transducers for applications where typically superconducting systems are combined with photonics. So we are talking about detectors, sensors for sensing, but also for communication. And Supreme will develop these technologies from their current status, which requires improvement of the stability and scalability of the processes, and we will demonstrate kind of key building blocks of different kind of quantum systems. So for quantum computing, we are about to demonstrate a 3D integrated quantum processing unit, and then a signal amplifier. So this is called TWPA, or French call it tuba amplifier, which is used for reading out the signals from the qubits. Then for sensing applications, we are looking especially in the SNSPDs, which are superconducting single photon detectors. And these SNSPDs can be used in different sensor applications, but also for communications. So for optical quantum communications, you need single photon detectors. So SNSPDs are there a very valuable component. And also transducers that enable quantum coherent transduction from the qubit signals, which are in kind of radio wave frequency signals, into the optical domain, so that we can connect superconducting qubits into optical quantum networks. The consortium is combining the best expertise in Europe in superconducting quantum technologies. We have 8 member states represented, and also this project is really focusing on the industrialization of the technologies. So we have actually more companies than we have RTOs or universities. Almost half of the partners are companies. We have, let's say, the most well-known startups and SMEs developing superconducting quantum technologies in Europe as partners, but we also have large industries like Infineon, which is then also a kind of natural foundry partner for scaling some of these technologies to industrial scale fabrication in the future. We have 9 RTOs, and then we have 3 university partners involved in the consortium. And the Supreme pilot line is coordinated by VTT, Technical Research Center of Finland, and I'm the coordinator. I will keep it quite short. I think you have already heard a lot of about quantum technologies today, so I will just summarize with the main goals of Supreme pilot line. So indeed, we focus on stabilizing these superconducting quantum technology processes so that we can increase the repeatability and yield of the components, and thus the chips and the quantum systems based on superconducting technologies. And why do we do this stabilization? We do it to provide pilot fabrication services for European customers, especially SMEs and startups, but also, of course, larger industries, RTOs and academia are seen as an important users of these technologies. And the way to provide this access to these technologies is to develop process design kits for the stabilized processes, and then provide these MPV, multi-project wafer type of runs for the external users, so that we can then help SMEs and also the innovation and research in this research institute and universities to grow, and the ecosystem to mature and get more business in these quantum technologies in Europe. And in the picture you see kind of the long-term vision for Supreme is that we will want to go from kind of single quantum components into a complex quantum systems, where we can combine different technologies and also superconducting technologies on a single multi-chip system here. So we see here in the middle, we see the actual quantum processing unit, and then we have so-called peripherals, the tube amplifiers, maybe a single flux quantum, so SFQ superconducting coprocessor, the SNSPDs for optical detection and transducers for communications. And all of these building blocks, even though they are fabricated with different flavor of technology, superconducting technology, they can be combined together on this kind of a multi-chip module, as we also develop the 3D integration methods for these modules. And with this one, I thank you for your attention, and over to you, Oxana.
Thank you very much, Pekka, and to all the others who presented, all the other coordinators who presented the pilot lines. And I think at this point, it would be great if we can welcome you all on stage and answer a couple of questions from the audience before we then switch to a presentation by Kristiaan Trefzger about the overall impact of the Quantum Act, of the CHIPS Act on the quantum chips. So we have first question is about the maturity level, and is there a real-time TRL, MRL status information available for all the pilots line components at the moment?
I can start from the Supreme and superconducting technology side. Yes, indeed, we have evaluated the TRL and MRL for all of these technology flavors, which I just presented. And also we have then set up goals for the increase of TRL and MRL for the duration of the whole FPA, so for the first and the second SGA. It's not easy to give a single number, because there are differences in those MRL and TRL levels. You could, for example, say that the TRL level of qubit processes for these QPUs today is very high, because it's already in use. So one could say that it's even TRL 8. but the manufacturing readiness level of the same technology is not that high because of the high variance of the and low yield of the fabrication. So we could be closer to MRL4 for the same technology, but in the application, it's anyhow TRL is much higher.
Thank you very much, Pekka. Let's see what Andreas could share with us about the ions. You're muted, Andreas.
Yeah, similar comment as Pekka, that for the proposal, actually, that's probably what Kristiaan also mentioned, it's actually required, or the target would be like TRL MRL6 after the 3-year first proposal in general to be reached by the pilot lines. I don't see any real-time status information available. I mean, it's not planned that we like keep community informed in real time about the readiness, but we clearly evaluate now the readiness we have, and it's quite different for different processes and different trap types we target, and try to reach it. So it's very clear defined then what we want to reach after 3 years. And also I can confirm, like also a comment from Pekka, that the readiness level, the manufacturing readiness level, which is the main target of the pilot lines to establish high manufacturing readiness levels, does not always reflect the TRL of actually the chips themselves, because we have some chips used in quantum computers, again, similar to superconducting, which were basically produced on single piece level, which is low MRL, very high TRL of the chips themselves. On the other hand, there were chips fabricated for ion traps on CMOS pilot lines, on CMOS, not pilot lines, CMOS lines, which then have never been made the step to go out of the lab because of the readiness of the chip design themselves.
Okay. Thank you so much, Andreas. And let us see what we could hear from Nicole about the diamond chips.
Thank you. So actually, I have a similar comment as Pekka and Andreas. So the TRL and MRL level of the, let's say, diamond technology at the material components and device, let's say, stages is not homogeneous. We have, of course, a plan to reach during the first SGA TRL and level of 6. The time frame of the first SGA is, for in our case, 3 years and a half. And yeah, so the goal is, in our case, is probably similar to what Andreas commented, to advance also the manufacturing readiness level at the material, diamond material. So the substrate, color center generated inside, components that will form the chip, and then the whole integrated chip. So all these stages have to be matured during the pilot line project development, and our goal is to reach within the first SGA TRL level of 6.
Thank you very much, Nicole. And now, as we heard from a few projects about the TRL and MRL level, let's go to a next question, which is dedicated about the collaboration between the pilot lines. So the question, is there a cross communication between these projects? And is there a good tips that works for collaboration sense and coordination efforts? I would welcome the Photon pilot line to reply on that, as I think this is the most connected to other pilot lines project.
Well, thank you very much for the question. It is very relevant, of course, because it is our ambition to produce the photonic chips that is relevant for all the other pilot lines, at least, and then use their input as for the specs and for the, and also the end users. I think the best practice for this kind of communication is personal acquaintances. So for that reason, I also am very happy with this meeting. There are already, of course, connections, but I'm sure we can improve them by meeting up. And while we have now getting in the process of formulating the SDAs, we should step up this communication. Thanks.
Thank you very much, Andreas, for commenting on this very important point. And connected to this question, we also have a question to Alexandra about the Q planet. And the question is about the on-chip laser, which is probably something that is addressed also in the photonics pilot line. So how do you tame the risk of duplication possibly of the efforts, or are you already aligned on collaborating on this point?
Thanks a lot for the question. Indeed, we are fully aligned. We have been working very closely with the photonic pilot line, notably to find a delineation between the two, in terms also on wavelengths, on lasers that are going to be used in one and the other one. And even in our respective proposal at the FPA stage, we have shown what is going to be developed into the pilot line of QPlanet and the one, and what is going to be then even reused from QPlanet to the photonic pilot line as well. Second, we also have different actors that they are actually in the two pilot line, several of them, and the exercise has also been done to really delineate the activities between the two pilot line and make sure that there is no twice the same activity done in each of the pilot line, and of course there is no duplication in terms of funding. So we are fully aware of that in this type of project, and we have been of course anticipating that since the FP8 stage. Thank you.
Thank you very much, Alexandra. And one more question to who would like to pick it up, and it's about the access model for the different pilots. For example, for the SMEs or research labs in Europe that wish to access the facilities or the development chips. So is there only commercial basis, or will there be also other opportunities?
So maybe I can take this one as well and pass to my colleague. It's okay. Of course, speaking here for startup as lead, so it's very important for us to have the access that is open. And of course, there is no such a thing that only a closed commercial access. Excuse me. It will also be open to others. This is going to be defined, of course, in the model that is put in place, but also, as you know, in the implementation that is requested already at FPA, but that will also be requested at SGA one, the way how we implement the project and how the result can be exploited and disseminated and reused by others. So this is something that is going to be taken fully into consideration as well. In the pilot line, at least in QPlanet, but I guess for my colleagues is the same.
Okay. Thank you so much for the answer. So open access is the key, and that's great. So we would close the question session at the moment with the final one, which is about the job requirements and workforce personnel that will be needed for this effort to be taken up. So could you comment on how many people should be employed for progressing with these pilot lines? Maybe we could address this question at the moment to Pekka. If there is an estimate for the human resources that would be engaged.
Well, I would say that way around, that we haven't considered the amount of people working, especially on the pilot line itself. But what we have considered, and this is now an example from Finland, where we have estimated the amount of people currently working in quantum technologies and what is the need for the workforce in the coming years. And we see a significant growth. So I don't remember now all the numbers by heart, so I don't maybe throw any exact numbers, but saying that we are in order of 1,000 people in Finland working on quantum technology related activities. So that includes companies, universities, RTOs from kind of pure quantum technology and also some related photonics activities. But and we see that this will double in a matter of 5 years. So this is the order of magnitude what we are talking about, and let's say that 1% of the European population lives in Finland, so you can multiply by 100, and you are what we are talking about on a European level maybe. So instead of talking about what is employed in the pilot lines only, I see that the impact and pilot lines enabling the access to mature technologies for companies who can then build products and grow based on these technologies will be more important.
Okay. Thank you so much, Pekka. And I must ask this question. What about the business case after the end of the project period for the continuation of the pilot lines?
Sorry, Oxana, because I could not raise my hand, but I would like also to respond on the job question if it's possible.
Absolutely.
So we did indeed in QPlanet already a projection on jobs on that question. So we estimate for the moment that it will be around, is expected, of course, that can change, around 350 jobs direct and more than 1,000 indirect jobs on that question. On the business model, I would prefer not to respond now to that question, because maybe also to say that we are starting the SGA 1 stage, and some of the information is still confidential on the business model and the exploitation. But perhaps just to say that this is the SGA 1 phase with increasing TRL, as you have been hearing so far. And then it will also be followed by an SGA 2, so 3 more years. So when we speak about business model and exploitation, this will go, I believe, after these 6 years. So it might be a bit premature to respond to that question now in this session, and also for some confidentiality, at least from QPlanet, I would prefer not to address it here. Thank you.
Okay. Thank you very much, Alexandra, for targeting those questions. And with this, I think we could stop the question session at the moment, because we still have one presentation to go through about the place of the CHIPS Act investment for quantum technologies, among other programs that the European Commission is carrying out. I'd like to invite Kristiaan Trefzger to the stage. And Kristiaan is the policy officer for quantum technology in the DG CONNECT and the European Commission in Belgium. Kristiaan, are you? Yes, exactly.
Yes, I'm here. Do you hear me?
Yes, very well.
Yeah, okay, good. Fine. Thank you very much for the introduction. I have the pleasure of the honor of the last word. I'm Kristiaan Trefzger, Policy Officer in the Quantum Technology Unit, and I'm happy to walk you through the rationale that guided us into setting up the pilot lines that you have heard, the 6th one that you have heard before, under the CHIPS Act. So I will structure my intervention in 3 steps, introducing first the context, the CHIPS Act, and then finishing with the quantum pilot lines that you have already heard. As you know, the quantum ecosystem in the European Union is very rich. Since 2018, we have the quantum flagship that has been structured into 4 main pillars: communication, computing, simulation, sensing, and metrology. And these pillars have actually inspired many other activities, either at the national level or international levels. So the flagship was quite successful because the idea was to transfer the technology from the lab to the market. And around the flagship, what you see here, there are many rotating activities that are testifying this transfer from the lab to the market. Like, for example, the EuroHPC joint undertaking where we deploy quantum computers, the EuroQCI where we deploy quantum communication infrastructure, etc. And on the bottom right, you see the CHIPS Act, which is the last, I mean, the new kid in the block with 400 million euros of financing. And I will concentrate on this in the coming, but before going into the details of the CHIPS Act, let me say that the most, let's say, advanced project in terms of industrialization and going to the market under the quantum flagship are these two ones that are called QPilot and QTest. And these are what we call experimental production and testing capabilities for quantum technology. So QPilot is for piloting and QTest is for testing that in turn nurtures the production and in a virtuous circle so that you have testing and production. But I'd like to insist on this project that we were able to push under the flagship, that these are still experimental production and testing capabilities, meaning that they have a lot of flexibility. And then we came with the CHIPS Act, with its 5 objectives that you see here that will be implemented and are implemented under the CHIPS joint undertaking, where one of the objectives is fully dedicated to quantum chips. So we wanted to do something more, a step beyond of what we did under the flagship in the bringing the quantum technologies from the lab to the market. And in particular, we wanted to focus on the prototyping, on the bottom line that you see here below, on the prototyping and, well, actually a step beyond the prototyping, on the pilot lines that are in between what you see on the left-hand side, so applied research, and the production at the industrial level. But before entering into this, we ask ourselves, what is a quantum pilot line? So I already presented QPilot and QTest very briefly, and but let me stress again that what we were able to obtain under the quantum flagship with QPilot and QTest is to focus on research with experimental lines, offering small volume of production and very high research and development flexibility. So if you get, for example, the production line under QPilot dirty with a different material, it doesn't really matter because it's part of the flexibility that the line offers. Instead, the quantum pilot lines that we wanted to set up under the CHIPS joint undertaking, so under the CHIPS Act, they are targeting more mature technology stages. We wanted them to align with the manufacturing process of the microelectronic industry, so to reach another step, so to increase the maturity of the production. And for this, as you have heard from some of the speakers before me, we introduced the concept of a high yield production. That is a typical term that is being used in the manufacturing readiness level and in manufacturing processes of the microelectronics. So the idea was to reach stability and reliability of the production, which is a necessary step if you want to go into full manufacturing of quantum technology components. And okay, so we reached the concept. This concept was very well understood also at the political level, but once the concept was understood, we then turned to the community and said, okay, so what are quantum chips and what should we focus on? And in this slide, you see a brief summary, well, of what is available out there, what is Europe capable and good in doing at quantum chips. And you see that there are several, like for example, on the top left, you see the superconducting qubit, which are chips that are necessary for quantum computing. Below it, you see a photonic integrated circuits BBA for the BB84 protocol, which is necessary for the quantum communication. In the center, you see the NV center that is used with diamond, that is used for sensing, for communication, for computing, etc. Or in the top right, you see Paul traps for trapped ion quantum computing. So in a nutshell, there are many different chips that cover all the 4 activities of the quantum flagship. So it was very difficult to choose where to focus on because there are so many different, and they also serve very different purposes. So what we did, and this is my last slide, we did an analysis on the maturity level of the different line that we were able to identify against the chips fabrication, so the manufacturing readiness level for the production of quantum chips. And so we were able to identify that you see here on the left-hand side 6 different technology platforms: the superconducting photonics, semiconducting trapped ions, diamond and neutral atoms that you heard before my presentation. And we made the exercise of assessing them against the maturity for production of quantum chips. And you see that the message that we came up with is that the green spot, which means high maturity for chips fabrication, is practically everywhere, at least in one of the verticals. So superconducting is very much mature for quantum processor and annealers in computing and simulation. Photonics is very much mature for QKD over long distances, etc. And semiconducting, even if we assessed that this medium in terms of maturity is very, very much close to the manufacturing of traditional semiconductor, which makes it very much close to maturity for production. So in a nutshell, all of the lines are mature at least in one aspect of the verticals for the maturity of chips fabrication. And so this is why we were able to launch the call for selecting 6 pilot lines under the quantum, the CHIPS joint undertaking under the CHIPS Act. I think this is all. I'm happy to have walked you through the rationale that brought us to the very nice presentation that you have heard this morning. So, and then Oxana, back to you. Open the floor for questions, if any.
Thank you very much, Kristiaan, for closing this marathon of the pilot lines that were selected under the CHIPS joint undertaking. And indeed, it was a very intense session and we went much over time, but I think a lot the participants who still stay with us and could follow until the very end. I think fair enough, the questions are being mostly been dedicated to the pilot lines. And we have a question about the cryogenics, but I think I will not address that to you. And there is one question that I would like to address you. So how can we ensure that the impact is maximized over the Quantum Chips Act across the entire European quantum ecosystem? What is your take on that, Kristiaan?
Well, thank you for the question. I think we did the best that we could. It took us practically a bit more than 2 years to decide exactly where to put our efforts. We consulted the community at large with several workshops at EQTC conference, at large conferences under the semiconductor topic. So I think we did our due diligence properly. However, you're never sure. The technology is evolving, and there may be something that we have missed out because it simply evolved in the last couple of months. So I think, by and large, we made sure to do something that represents what the community needs, but still we have some flexibility for future activities to take into account new development, and especially very recent development that we were not able to capture at with our extensive consultation that we did during the past 2 years. I must add to this point that we are so under the CHIPS joint undertaking, we are together in the same boat, let's say, with the member states. So what we are financing here is expected to be financed 50% by national funding agencies, so by the member state. So we can also get from that perspective additional inputs on the national level, on the peculiarities of the national and even regional needs of the quantum ecosystem. So in a nutshell, I think we did our due diligence, and we are still open for novelties that may be developed very recently.
Thank you very much, Kristiaan, for elaborating on this question. And I think we are good. And
I just see one last question by Pepijn directly, if I read it correctly. So, Kristiaan, if you can help us with any insight in the chances of the EU launching a Quantum Act.
Yeah. Okay, I assume it is a reasonable question. I assume you're curious. Also, Oxana mentioned CHIPS Act, Quantum Act. What is this? So, unfortunately, I cannot share too much. What I can say is that we have a clear timeline. Next week, we will release the quantum strategy together with our executive vice president of the European Commission with an event that will take place in Brussels, and it will be released publicly. I think it will be either Tuesday itself or Wednesday next week. Of course, we have developed the quantum strategy knowing that there will be a Quantum Act, and knowing that the Quantum Act will be, let's say, the idea is to have it either by the end of this year, 2025, or early 2026, which is maybe what is more reasonable to expect. There are several areas of activities. There are several points that needs to be taken into account, notably the fact that we have witnessed in the past years, and I'm sure you have witnessed also in the past years, the fact that there are several national strategies in quantum. Each member state is jumping into quantum activities with their own strategy, with their own ideas of what are their priorities for investing in quantum technologies. Of course, this is beautiful because everybody has I mean, the realization that quantum is having an impact and quantum is important, and member states are getting into it is essentially it's very refreshing from my side, from the point of view of the Commission. However, if we want to have a difference, if we want to make impact in quantum technologies, I think we need to coordinate all this effort. We cannot act as silos. We cannot be in each one doing the same thing as an independent way and replicate what a member state does in another member state. So we need something like that. We need a strategy that provides the high-level ideas of what are the issues that we have in Europe, what is the vision that we would like to achieve in the coming years, and we need an instrument to implement this strategy, which will be the Quantum Act. I cannot go into more details than that.
All right. And the very final question in the question and answer set that would be addressed to the pilot lines, but unfortunately the superconducting pilot line has left us. Will some of the quantum chips require cryogenic operations? And of course, I think the answer is yes. And if yes, how does it impact the pilot line?
I can maybe comment for the ion traps in that yes, not all, but some of them require cryogenic or ultra high vacuum conditions. And how it reflects the pilot line, it reflects in the specification requirements on the chips. So of course, if you have like heterogeneously assembled chips, that has to be cryocompatible. The materials have to be cryocompatible. Ultra high vacuum has to be considered. On the other hand, we do not have any like cryo equipment and periphery here, because the target of the pilot line is clearly the fabrication of the chips to be used under cryogenic equipment. It's not about developing any cryogenic equipment or things like that. At least for the ion traps, that's the case. We have to consider this environment, but we had the discussions about basically also developing like cryogenic environment and miniaturized cryostats, but did not include any of these topics there.
Thank you very much, Andreas. I see Nicole coming up and probably wanting to add something.
Yeah, just a small comment about the Diamond Quantum Pilot Line. For most of the use cases that we can identify, especially in the area of quantum sensing, no cryogenics is required. So this kind of technology allows for room temperature operation. And also use cases in quantum computing, let's say, allows for architecture, room temperature architecture, although there are also cryogenic based architecture for quantum computing. So this that's all. Thank you.
Thank you so much, Nicole, and to all the speakers again for staying with us until the very end. And it was a great and intense session, and I wish good luck to all the pilots on their development.
Thank you, Oxana, for organizing.
Thank you.
Thank you.
Thanks a lot.